We continue to look at different classification models. In our previous videos, we looked at k-nearest neighbors, generalized linear models, support vector machines, and naive Bayes. So let's look at decision trees. And then in the following videos, we'll look at random forest and gradient boosting machines. So the key is to know when to use which classification method. And so since this video is going to focus on decision trees, let's just look at when you would use decision trees. So if you're unsure as to what predictor variables you should use, then you should use decision trees, random forest, or gradient boosting methods. If your groups are unbalanced, so if we look at the number of training data that is in one label versus another, and they're quite different, then we should use decision trees, random forest, or gradient boosting machines. If you have more than 2 predictor variables and you want to show visually the classification system, then you're going to need to use decision trees. And we're going to look at decision trees in just a moment. The other two, random forest and gradient boosting machines, are a form of decision trees. They can't be visualized like the traditional decision trees approach. But if you're quite concerned about false negatives, you should be using random forest. And if you have a very large data set with tens of thousands of data points per variable, then you should be looking at the gradient boosting machines. But we're going to focus here on decision trees. And the benefit of decision trees is it allows us to visualize the classification when we have more than 2 variables. That's because we can classify or we can visualize when we have 2 variables, because 2 variables, right, we have an x-axis and a y-axis, and we can show then, like we can see here, there's the blue labels and the green labels, and so we can then visualize that 2 dimensions. But in order to visualize more than 2 dimensions, really, of all these different methods, your only choice really is these decision trees. So let's look at decision trees. Now, in data analytics, back before machine learning, there was something called decision trees, and this was that decision trees. So it was about looking at decisions under uncertainty. You had a new product. Should you terminate your work on the project? Should you invest in research and development? Should you then terminate the project, or should you invest in marketing? Should you then sell the product? What if it's a good economy versus a bad economy? So this is a decision tree in the pre-machine learning, pre-AI world. This is a bit different than the decision tree we're using in classification. So in our classification model, we are using decision trees, but they don't look like this, they look like this. And so there's a couple pieces to the decision tree we need to know about. The boxes are nodes or events. So if we think about a survey, right, we had our survey to our union and to prepare for bargaining. And so we had our survey to our union members, and we asked about their opinion about where they work, about their location. And when we look at that Likert scale, 1 to 5, they could have picked 4 and 5 more positive. They could have picked 1 and 2 more negative. So here we have an event, their opinion about location, and then we have a branch, the response to that question, positive or negative. Then we have another node, this box, this event, which is what's their opinion about the number of hours they work. If it's more positive, so again, Likert scale, 4 and 5, then we can classify them into one group. That group had a positive opinion about the location and a positive opinion about the number of hours. We could find another group that had a positive opinion about the location, but a negative view about their number of hours. We'll call that group 2. Then we have another group that has a negative opinion about the location they work in, but they have a positive opinion about workplace safety. So they don't like the location for some other reason. So they're group 3. And then we have an opinion about location that's negative and an opinion about workplace safety that's negative. So here we've classified into 4 groups. Now, with the classification model, we have labels. So we already know group 1, 2, 3, and 4 exist. Okay, they already labeled. And what we're doing is finding the tree, their responses to multiple questions that show us who that group is, that identify that label. And I'm just going to move my face for a second because you should see on this slide there's a couple things to consider as we look at our decision tree. We need to look at the maximum depth of the tree. So here what we have is we just have 2 rows of nodes. That's the number of layers. So how many different combinations of questions to get at our groups? And you can make a more complicated decision tree with lots of layers. And so we can specify how complicated our decision tree is going to be. How many different layers or different rows is it going to be? Or is it going to be very simple like this one here it's really 3 questions from the survey, and one question applies to 2 groups and another question applies to the other 2 groups. The other thing to consider is the minimum sample split. So how many data points at a node before it branches off into something else? So what we look at is opinion about location. How many people responded to that question? Well, then if we hive off those who have a positive response, how many people is that? If that is too small of a group, then we're going to not branch off anymore. We're not going to look at the positive and negative for the next question, opinion about number of hours. So we would decide what's the smallest the groups get before we stop splitting anymore. So that's the minimum sample split. All right, I'm going to put my face back down here. So we're looking at decision trees, which is a supervised learning approach. And the benefit of this method then is we might have lots of different variables, and we're really not quite sure which are the best. We should be doing exploratory data analysis first. We should be doing our inferential statistics to see if there are relationships, our one-way ANOVAs to check and see if the labeled groups really have a statistically significant difference in some of these Likert scale questions, the interval ratio type questions. We should be doing tests like Kruskal-Wallis to see with the ordinal. So we should be testing out that statistical significance and exploring the data with visualizations first to make sure we're on the right track for our classification. But if we're still really not quite sure which variables to include and not include, the decision tree allows us to put in a bunch of variables, and then it will see where it's appropriate to use them to classify. All right, so with decision trees, the model is going to determine which predictor variables are really relevant. It can be used with binary labels or with multiple labels. So like the K nearest neighbors, it can be multiple labels. Like the general linearized model, it can be binary, yes, no. And when it comes to the predictor variables, they can be ordinal, interval, or ratio. So they can't be nominal. Only naive Bayes allows for nominal, but they can be ordinal, interval, or ratio. Now, in terms of the decision tree, it does something called a Gini index. The Gini index measures the probability that a particular data point would be misclassified if it were randomly allocated to a branch. The nodes are selected by the algorithm to minimize the Gini index. So when it's looking at which branch it should fall into and how it should be organized, which variables are relevant, it's going to look at would that data point be misclassified if it had separated and made these nodes different, if the branches and the cutoffs on these branches had been different. Okay, so it's looking for the tree that minimizes that Gini index. All right, the challenge with the decision tree is that it's going to be highly susceptible to the order the variables are loaded into the algorithm. And so that means that when you do separate out your testing and training data, what happens to be in the testing data is going to have a lot of impact on the tree. And so what we'll find is when we kind of re-roll it, when we run it again, you can get very different responses each time. And so we'll talk about ways to improve our decision tree, how to tune the hyperparameters, how to improve the method of it, after we discuss also the random forest and the gradient boosting machine. So right now we're just going through the basics on decision trees. So here's an example of a decision tree. You can see the Gini index listed there. And so when we look at this, the way a decision tree works is that here's the first node, and it's looking at question that it's identified as 3 in what's loaded. So that's actually in this particular data set, question 15, that asks whether respondents are satisfied with their location. It happens to be the third variable that's entered in into the when we give it the variables to look at. So it's just called it 3. And so what it's saying is for question 15, it's looking at, is the response less than or equal to 2.5? So if you're less than or equal to 2.5, you are not satisfied with the location. And so if you're not satisfied with the location, then you go here. And then we look at what it's classifying as X5, which is question 20, based on how we loaded the data in, and says that if question 20 says whether respondents are satisfied with inclusion. Well, if the response was less than or equal 3.5, so it's negative or neutral, then that leads us to here. So then it looks at what it's calling X4, which is whether respondents are satisfied with the workplace safety, which based on how we entered in the data here is question 18. And it's looking at here, if when it comes to question 18, you are not satisfied or neutral, that puts you here. So at the end of this, as we go down the decision tree, this particular group here has a size of 10. And in this particular case, what we're doing is we are trying to predict. There are 2 labels. And so when it says value here, what it's doing here is that this first spot is for one label and the second is for the other label. And so what it's showing here is that this particular group is all 10 fall into that second label. So if we look at this here, these endpoints, what it's creating is 11 subgroups. And in this particular decision tree, it's what they're trying to classify as south versus not south in our bargaining survey. And so we can see this group here. The green ones are the not south, right? That second position. And the blue ones are where you end up with south. And then this black one here, it's inconclusive. So you notice how it's put numbers into both positions. It was unclear as to what their location is. So here, you can see with the decision tree, we started off with and I'm just going to go back one here. We started off here where the satisfied with location, less than or equal to 2.5, so not satisfied. And then we said, what about question 20, satisfied with inclusion? Well, if they were less than or equal to 3.5, they were this one here. But if they were greater than 3.5, then it's this group here that ended. And so those who were satisfied with inclusion became this group. And this group here is part of our blue. And so the blue ones here, we can see that we have our south location, and then the green here are our not south location. So the decision tree goes through and creates these different subgroups based on how the individual answered. In this case, here's 3 questions. And then this one here, if it was greater than 3.5, there's another question which determined if they were this subgroup or that subgroup. And so you can see on this route on the decision tree, we have this question, we have this question here, and then we further it down, narrow it down to even higher values, put you here. And so you can see it can look at multiple questions, and it can come back and it can narrow it down and look at even smaller ranges of those same questions to find our subgroups. So we're classifying them here, these subgroups, there's 11 subgroups, but some of the subgroups are labeled as south, some of them are labeled as not south. So our whole goal here is to identify what combination of answers to questions would tell us that they're at the south location or not the south location. So how do we do this? All right, let's go into our Python code. And just a reminder, you can do this code. Go to drstephpowers.github.io/BIA. We are working through the classification workbook. So click on classification, and you will need not only the Python workbook here, which you can open in Google Colab by clicking here, logging into your Google account and saving it. But also you're going to need a couple data sets. So the one that's bargaining related, we're doing bargain numeric, which is right here. So save that to your Google Drive and then mount your Google Drive in Google Colab and link to and call the data from bargain numeric. We're also looking at the CRM clean. That's the customer relationship management data that's been cleaned. And you'll also find that one right here. So put those into your Google Drive and then link your Google Colab file to your Google Drive and call your databases, your Excel spreadsheets. So we've mounted, we've called them. All right, let's go and find our decision trees. And we'll back up a bit here. Lots of trees. Gotta find that spot. That's the problem. Too much here. All right, let's start with decision trees. If we're going to do a decision tree for a binary classification, right? So recommend, don't recommend, or in this case, south, not south, then we can use the precision score, the recall score, the confusion matrix. So in this example, we'll pull those. And then for all of them, because this is labeled data, we can measure accuracy. So we're going to pull the accuracy score. And instead of pulling out data ourselves that will be the testing data, we are going to randomly pull and have it separate out the testing and the training data. That's what this model selection train test split is. And then for the decision trees, we are going to need decision tree classifier. So sklearn.tree. Decision tree classifier, and to get to there we're going to do from sklearn import tree. So basically it's nested from sklearn import tree, from sklearn.tree import decision tree classifier. This allows us to call the decision tree classifier and to help and to make the visual tree that we want. So we need both of those. And we are using data frame 2. Data frame 2 is the bargaining survey, and you'll notice in this version of the bargaining survey, if we're pulling it fresh, so we initially load data frame 2, you'll notice that it has question 23 coded as 1, 2, 3. We need to turn it into a binary classification, so we're going to create a new variable called south. It's going to be an exact copy of question 23, but then we're going to replace the numbers so that the north location is 0, the south location equals 1, the east location equals 0. So it's ones and zeros. If you'd rather do 1 and 2, so that you have 1, 2, 1 as your labels, you can do that too. It's just that you can only have 2 options. Okay, so we're going to take this and we're going to replace that. So if we looked at it now, df2.head, now you can see we have this extra column where we're labeling when 23 equals 2. You can see there's a 1 there. So we're looking at south, not south, because in our exploratory data analysis, we're starting to think maybe there's some issues with the south location. And so we're trying to see, can we actually identify the south location based on certain characteristics? So we're going to create a decision tree. Oh my goodness, I have an itchy nose. And we're going to have it separate the data. So rather than specify this is the training data and this is the testing data, we are using our command here that we loaded called train test split. And we are going to do xtrain xtest ytrain ytest equals train underscore test under split. And here we're going to take a bunch of variables. The benefit of a decision tree is that it will identify what parts of these variables are relevant. So we'll give it a handful to choose from. And it might find that some of these variables are not relevant, and some of these variables are only relevant in a certain branch of the tree. Okay, so question 2, question 13, 14, 15, 18, and 20. So let's go and take a look at the original data. So question 2 was, what type of contract do you have, part-time or full-time? The benefit of a decision tree is decision trees can use nominal data. Okay, so remember, naive Bayes is the only one so far that can have nominal predictors. Decision trees can have nominal predictors as well. All right, so we said 2, and then 13, 14, 15. 13 was, how satisfied are you with the amount of hours that you work? 14 is, how satisfied are you with the time of day in which you work? And 15 is, how satisfied are you with the location where you work? So we'll put in 13, 14, and 15. Oops, wrong data set. All right, 2, 13, 14, 15, 18, and 20. So let's go to 18 and 20. 18 is, do you feel your workplace is safe? So here we have a Likert scale. And 20, my workplace is inclusive. Again, Likert scale. So notice what we have loaded into our decision tree is we have one nominal, which is coded here, 1, 2. And then question 13, 14, 15, 18, and 20 are ordinal Likert scale opinions. And what we're going to be predicting is we're going to be predicting the label south, no south. So we're using that column called south. We're using our 80-20 rule, so 20% test, 80% train. And we're going to stratify over south because we want to make sure that the south, no south appears in both the testing and the training data. All right, let's load that up. So then, just like every other classification model, what we do is we say, what is the model we're using? So we'll call it D-tree, and it's decision tree classifier. Then we fit the model on our training data, so X train, Y train. Then we're going to predict our values. So let's predict south, no south for our data set here. So in the predicted, we have 3 that it's predicting are south. Because we are doing a binary classification, we can test out more than just accuracy, but let's start out with accuracy. So in this particular run, our accuracy is 85%. Now, please note, I did not put random state equals and then a number. If we did that, then we could all get the same decision tree result. We didn't do that here because then you can see that when you do this, depending on what ends up in the test and what ends up in the train, you end up with different accuracy and a different confusion matrix. So let's look at this one and we'll rerun it and then we'll do it again. All right, so let's create this confusion matrix. Let's display it because it always looks prettier as a chart. So notice here we have 3 that are predicted to be south and are south. We have 8 that are predicted to be not south and are not south. We have 0 that were predicted to be south but weren't. So this is the false positives. And then here we have 2 that were predicted to be not south but are. So we have 2 false negatives. So notice if we calculate precision and recall, the precision is 100% because there were no false positives, and our recall score is 60%. Okay. We can use that tree command that we imported and use plot underscore tree, and then D-tree was the name of the model, right? D-tree is what we used here. So when we do this, tree.plot underscore tree, D-tree, plt.show, then we get our decision tree. So what this decision tree shows us is that we have our variables. And so when it comes to the things that are in the X, so here we have our 6 variables. And remember, in Python, the counting starts with 0. So Q2 is 0, Q13 is X1, Q14 is X2, Q15 is X3, Q18 is X4, and Q20 is X5. Let's go back to our tree. All right, when we look at this, we see here's an x5, here's an x4, x3, x2, x1. Notice there's no x0. So it did not use the nominal data of part-time and full-time. Okay, part-time and full-time really did not help them figure out whether it was south or not south. It's always going to prefer variables that have more information. So interval and ratio are typically going to show up, nominal less so. Now, it's quite possible you have a decision tree where all of your predictor variables are nominal, in which case it's going to choose nominal. But it's going to look for where the most variability is to help it figure out the classes. And so if it can get enough information from the interval and ratio, if there are any, here there's not, if it can get enough from the ordinal data, then it's going to just exclude those nominal ones. If you have nothing but nominal data, then of course they'll be included. All right, so let's take a look at this. So remember, these are locations, index locations. So just because I'm totally going to forget, I'm going to write this down. Question 13 is 1, question 14 is 2, 15 is 3, 18 is 4, and 20 is 5. All right, let's go back to our tree. So it's going to start with question 15. So question 15 was, are you satisfied with the location where you work? Well, that question really should have the biggest impact on what location you're at. So it makes sense that it would be loaded first into the system. Those who are less than 2.5, so it's Likert scale, so that leaves 1 and 2. If they're 1 and 2, so they don't like their location, it pushes them over here. And then we go to question 14. Question 14 said, how satisfied are you with the time of day in which you worked? So here, question 14, if they were very unsatisfied, less than or equal to 1.5 just leaves 1, then they are this group right here. And so then we have this group here. If they went with more than 1.5, then we look at question 4, which is question 18. Question 18 does, do you agree with the following statement? My workplace is safe. If we look at there, is the workplace safe? If they said that it's less than or equal to 3.5, then they're going to end up here. And there were 9 that ended up here. If it's more than 3.5, so those who strongly agreed and strongly agreed, so 4 and 5 on that scale end up here. So notice this one has values in both spots, so it's really not clear. That's the uncertain. They don't know if they are south or not south. Okay, and so you can work through and you can find these different combinations. It shows you how many individuals fall into that group. And then it shows you in the value here, the left and the right, that's your 2 classifications. Okay. So we can see then the south and not south. And our classifications were 0 and 1. So this one should be the not south and 1 should be the south. If you made it 1 and 2 and 1 was the south, then that's going to be the one that comes first. And then the not south would be the other. So it depends on how you coded it in terms of interpreting that output. Okay. All right, so we did this with a binary classification. Oh, I just want to run it one more time to show you it changes. So let's go back and let's re-separate out our training and our testing data. And I've here just specified a random state. That way, if you do it the second time around, you should get the same as me. If you decide to specify that random state, but it's probably not the location of the first prediction. So we do this, we see if we can get different predictions. The accuracy of our previous model was 85. Notice the accuracy of this model is 69. So it really does depend on how it loads the information into that testing and training data. That's really going to change the results. So here, when we display this, notice that we now have a false positive, whereas the last time around we didn't. Okay, which means the precision score in this particular one is not 100%. and both the precision and the recall have gone down with this particular scenario. So again, after we do our videos on random forest and gradient boosting machines, we'll talk about hyperparameters and tuning to improve your model, because these three types really are going to change so much every time you do your random pull. And so we'd actually get a different tree for this. So you can see the tree is different. It's still starting with question 15. Now it's going to question 13 next. So these may change when you re-roll them. Now, before we go into that, let's just show how decision trees can be used with multi-labels. So the previous example was with a binary label. Here, let's look at a multi-label. So we're going to use the same packages: tree, decision tree, classifier, train, test, split, accuracy, score. We can't use precision and recall because we have a label that's not binary. So what we're going to do is we're going to look at data frame 2, so still our bargaining survey, still question 2, 13, 14, 15, 18, and 20. So same questions as before as predictor variables. But let's change this to question 23, which then is not just south, no south. Now we are north, south, east. Same 80-20 split. We stratify across question 23. So there are north, south, and east in both the testing and the training. And if you want to see if you can get the same results, let's just specify our random state and comma. All right, you can pick whatever number you want. So if you have a favorite number, you can set the random state for all of these, and that way if you go back, you can set the same random state and get the same results. Or you can turn the random state off and just randomly generate to see how it changes depending on what you do. So we call the model, we fit the model, we do our prediction based on our test data, we check the accuracy of our model. This one is at 54%, and we generate the tree. And what you notice is the tree is a lot smaller and a lot more detailed. And that's because we had like 11 subgroups when we were just looking at south, not south. Now we're looking at, is it north, is it south, is it east? Well, as much as these charts are a little interesting to kind of see how it's separating out, what we really care about is the prediction. And so if you were going to use this model, so it had an accuracy you were okay with, then what you would do is you would put in new information for question 2, 13, 14, 15, 18, 20. Either that's because you're looking at if they answered this way, what would this say about the location? Or maybe you have some additional information, additional people who filled out the survey. You could identify what location they were at. So this here predict piece, we use it with the test data to see how accurate it is. But in order to actually use a classification model, we would then want to predict other labels for new data. And so we're building this algorithm so we can use this predict command for new data. All right, so we have created our tree here. Now, this tree, right, it's got a lot of levels. We could specify the max depth, how many levels we want. So we could simplify this model so that it's not so many levels. To do that, when we are calling the initial classification model, that is where you would specify max depth. So here we would say we only want this to be 5 rows. So max depth equals 5. Then we fit it. Then we predict it. And then we can run the accuracy here. This accuracy here is 62%. It's running on the same test and train. So you can see that we can simplify this model without making the accuracy be worse. And in fact, right, that accuracy is a bit improved there. So the new one, if we were to plot that new decision tree, then this new decision tree, see how it's much simpler, okay? And so it's only 5 levels. 1, 2, 3. Ignore the first one, or ignore the last ones because that's the groupings. 1, 2, 3, 4, 5. And the last are going to be all your little subgroups that you're going to see here. And if you can see, there's 3 spots. And so we have 1, 2, 3. So it's telling you then if it's north, south, or east, depending on how it puts them in there. So we can use our decision trees with nominal predictor variables, ordinal, ratio, or interval. We can predict binary classifications, so south or not south. We can have multiple label that we're predicting, so north, south, or east, with our decision tree. And the benefit of our decision tree is that we can visualize multiple variables and use it when we're unsure exactly which variables we should be using. The downside to decision trees is that every time you run the model, it's going to be slightly different tree. It's going to be slightly different accuracy. It does change quite a bit based on what's loaded into the test and train data and the order in which information is loaded in. So you can get quite variability in both the model you create and the results of it.